Okay, welcome everyone. Hope everyone is fine after the earthquake today. And so today we're very happy to have Emmanuel Schaan, who is visiting us from the US. And so Emmanuel is from France originally, and he did his PhD at Princeton and got his PhD in 2017. After that, he moved to Berkeley, so the Lawrence Berkeley National Lab as a Chamberlain Fellow for 5 years, from 2017 to 2002. After that, he moved to SLAC, the SLAC Accelerated National Lab at Stanford, as a staff scientist. And so Emmanuel is an expert on cosmology, connecting theory and observation, specifically working on CMB experiment technology surveys. So today he will be telling us about backlighting the universe by the CMB. Okay, let's welcome Emmanuel.
Thank you very much, Ethan, for this nice introduction. And thank you all for having me. I'm really delighted to be able to visit the Institute for the first time. It's also my first time here in Taiwan. And I do hope everyone at home is safe today with earthquakes. So I'm delighted to be able to tell you about some of the research that I and my group have been doing in the last few years. And like Ethan said, this is about using the cosmic microwave background, this first light from the Big Bang, as a backlight for the universe. And so the picture I'm trying to paint here is that the observable universe really is a shadow theater in which the galaxies are the protagonists, and the cosmic microwave background, the CMB, this first light from the Big Bang, is the backlight. And by illuminating the galaxies with this backlight, you actually get to reveal some of their properties that you wouldn't be able to see otherwise, much like a watermark on a banknote that you would put in front of the light. So this talk is about combining CMB and logical structure, or why, if you have galaxies at hand, you should put them in the microwave if you want to learn about them. So to get started, I thought I would start with some background and motivation. And so I will start with a summary of the history of the universe. And so here on the left, you can see the Big Bang 14 billion years ago, and all the way on the right, this is us here today. And there's a lot we know about the history and the composition, the evolution of the universe from many, many, many different observables. But for the purpose of this talk, I'll be focusing on two. The first one of them is this cosmic microwave background, this first light that was emitted 400,000 years ago when the universe became neutral for the first time. And so when I think about the cosmic microwave background, what I think about are the initial conditions of the universe. When you look at the CMB, you are really seeing the big picture of the universe. Now, the second set of observables that will be relevant for this talk are much closer to us today. They are late-time observables, and I can lump them together in this term of large-scale structure of the universe. This refers to the fact that if I look at the distribution of galaxies or matter in the universe, if I put a dot every time I see a galaxy, those are not uniformly randomly distributed, but instead they're clustered and they form together these clumps, these balls and filaments and halos. And when we look at this large-scale structure of the universe, what we see really are more like the final conditions of the universe, what the universe is today. And so much of the game of cosmology has been to try to match the statistics of the initial conditions in the CMB with the statistics of the final conditions in the logical structure. And if you're able to do that, then you may have a good model for those 14 billion years of evolution under gravity. And at the moment, we have such a good model for the universe that we call the standard model of cosmology. It fits very well all the existing observables, so you might think of it as a great success. However, it relies on a number of ingredients which are not part of the standard model of particle physics. So one is dark energy, this mysterious component or force in today's universe that's responsible for the accelerated expansion of the universe. The other one is this dark matter, or that matter that does not seem to interact with light or really in any other way than gravitationally. and which we know had to be present at the time of the CMB and already clustered back then in order to have enough time to form today's galaxies. And finally, if explaining the statistics of the initial conditions is something you would like to do, then our leading paradigm for it is something like inflation, which again is yet another force in the universe, which is not seen in any other way than this. So the appeal for me of cosmology is that you get to use the universe as a fundamental physics laboratory. And in many ways, if you want to do fundamental physics, the universe is a terrible lab because you don't get to redo the experiment and turn the knobs. But there is one way in which it is the very best lab, and that's as far as gravity is involved. And so by looking at the universe as a whole, we get to probe gravity. By probing gravity, we get to see all of this physics that's beyond the standard model of particle physics. And in the next few years, by combining observations of the CMB and the low-scale structure, the prospects are good for learning about these. For example, what is the energy density of dark energy as a function of time? Does it evolve like a cosmological constant? Or if not, does this hold clues to what it might be? What are the properties of dark matter? Does it interact in any other way than gravitationally? Does it have any temperature at all, or is it fully cold? And the particle physics of inflation. So how many additional fields or how many additional forces basically had to be there? What were their interactions? At what energy did all this happen? So by using the CMB and low-scale structure, the hope is to make progress on these questions in the nature of dark energy, dark matter, and inflation, which are perhaps some of the most important questions in all of fundamental physics. Now there's another question that we have hoped to make progress on, another particle physics question that I think is really exciting, and it has to do with neutrinos. So neutrinos are some of the most abundant particles in the universe, almost as abundant as photons, and yet there is still very much that we do not know about them. And one quantity in particular that I'll think about is their masses. And one way in which cosmology can tell us about their mass is that anything in the universe that carries mass or energy contributes to the mean energy density of the universe. And this affects expansion, which affects the clumping of this low-scale structure. And so really by using low-scale structure observables, we can really weigh those neutrinos. So if you look at those simulations, here are two visualizations of the matter density field. On the left, in a case where neutrinos will have no mass. On the right, a case where they do carry mass. And if you compare these two, you might see that they look very similar. The main difference being there's a bit more yellow here on the left than on the right. That is to say that giving masses to the neutrinos causes the structure on the small scales to be suppressed. And this effect is one that upcoming large-scale structure and CMB experiments should be able to measure. To give you an idea of the size of the challenge, how hard or easy this problem is, we know that today neutrinos have to be at least 0.5% of the matter density in the universe. That we know because of neutrino oscillations. We know they have to have some minimum mass. And so naively, you might think if you're trying to detect neutrinos, which are 0.5% of the matter density in the universe, you would need to measure the large-scale structure to 0.5% precision. But in fact, nature is being kind to us here because not only is this 0.5% of the matter non-clustered, the fact that it's non-clustered has a gravitational effect on the rest of matter, and this enhances the effect by a factor 8. And so the fact that neutrinos have been there for a long time not being clustered affects the rest of the matter. And so at the end of the day, the effect we're trying to measure is a 4% suppression of clustering. Now 4% is within reach of current atomic experiments. So I hope I've given you some motivation for looking at cosmology, CMB, and low-scale structure. So learning about dark energy, dark matter, inflation, the neutrinos. And here I would like to tell you how I'm trying to go about this. So if we go back to this timeline of the universe, I told you that you could think of the CMB as telling you the initial conditions of the universe, that baby picture of the universe. And that's mostly true. That's true for all of the CMB photons that have traveled throughout the whole observable universe without noticing anything. So these are the photons that just traveled in a straight line and reached us today. But that is not the fate of all CMB photons. For one, the CMB photon's path can be deflected by the gravitational potentials of the Gaussian structure. So the fact that galaxies live in dark matter halos that have mass, that mass pulls on the light. So this is a class of effects. There's a bit more than lensing, but lensing is the main one. And you can think of them as sort of shadows of the mass. So I call them shadows in the sense that they are imprints of the mass onto the CMB. So that's a bit loosely speaking. Another class of effects, which is not gravitational, is actually instead scattering. So some of those CMB photons, we know from Planck, about 6% of them, instead of traveling all the way and reaching us, do Thomson scatter with free electrons in the gas around galaxies. And this imprints another type of shadow, a shadow that I might call shadow of the gas. Those dark blobs around galaxies. And those tell you about how much gas, how much ordinary matter there is around those galaxies. This is particularly useful because, as I'll explain in a bit, there is much more ordinary matter than what we see in the starlight of galaxies. And this offers a unique way to probe all that matter. So really, in this manner, you are using the cosmic microwave background no longer as a probe of the initial conditions of the universe, but instead simply as a backlight in front of which you're trying to detect shadows, gravitational shadows and scattering shadows. So in that way, the CMB becomes a Gaussian structure. There's a reason why now would be a good time to combine CMB and Gaussian structure in this way. And one of them is that there's a number of high resolution, high sensitivity CMB experiments that are coming online. And I apologize, this timeline is already outdated, but I'm a member of the ACT collaboration, the Atacama Cosmology Telescope, which is now done collecting data and analyzing it. And one of the successors that I'm particularly excited about is Simon's Observatory, whose observations, so the part that I'm interested in, will actually start at the end of 2024. So fall 2024 is when this data will arrive. And finally, towards the end of the 2020s, CMB-S4, stage 4 cosmic microwave background experiment should be coming online. Those will bring a lot more sensitivity than current experiments. They will bring high resolution, and this will be really useful for detecting those shadows, the mass and the shadows of the gas. But not only do you have those impressive CMB experiments coming online, there's also a number of exciting Gaussian structure surveys. I am a member of DAISY, the Dark Energy Spectroscopic Instrument, which should be releasing its first year data very soon, over millions of galaxies with spectroscopic reference. So really dramatically increasing the size of existing spectroscopic catalogs. Another experiment I'm particularly excited about is the Rubin Observatory, the legacy survey of space and time. We expect data collection to start on this telescope again at the end of 2024. So the next year and coming year should be really exciting. And I know people in the audience are also working on SPHEREX, a really exciting satellite that should launch soon. As I've heard, it will map the full sky. So a lot of exciting galaxy catalogs, which one can then combine with CMB experiments for this kind of research. So that's all I wanted to say about the context, the motivation, how to use the CMB as a Gaussian structure probe, and why now at a given time. And so for the rest of the talk, I'd like to focus on these two types of shadows and tell you about some work that I and my group have been doing on these two effects to try to make progress. If there's any questions so far, please feel free to ask. if not, I'll get started with those mass shadows. And of course, as always, please feel free to interrupt if anything is unclear or wrong. Mass shadows or gravitational lensing of the CMB and how to improve those estimators. So first, I thought I would start by explaining what cosmic microwave background lensing is in a bit more detail. And the cosmic microwave background, again, refers to the fact that CMB photons do not just travel towards us unaffected by the logical structure. In the contrary, their paths are deflected by the presence of gravitational potential around matter and galaxy. To give you an idea of the size of this effect, these are small deflections, or arc-minute deflections. However, those deflections are coherent on larger scales, order degree. These are the typical coherence length of the logical structure. And this degree scale also happens to match the angular size of quantum hotspots. The effect of lensing on the CMB map is purely a remapping. It conserves surface brightness, which means that the lens temperature that you see here is exactly the lens temperature you would have seen there, where the difference between here and there is this deflection curve. And in the simplest regime, which is relevant for pretty much all experiments today, the deflection field, which should be a 2D vector, is actually entirely determined by one scalar field. The gravitational potential, projected gravitational potential, or this lensing convergence. In the rest of the talk, I'll be talking about lensing in terms of this convergence, but you can think of it as this is the scalar field that determines for you the lensing. So to show you a bit more visually what CMB lensing might look like, here's a typical map, a simulated map of the convergence field, where you can see the axes in degree, and you can see the red and blue showing you basically projected underdense and overdense regions in the logical structure. Now, what does this convergence field do to a CMB lensing map? To a CMB map. So here's a simulated unlensed CMB, and here now is the corresponding lensed map. And so if I flip between the two, hopefully you can see that those maps are not exactly equal. Now, ideally you would want to see the unlensed map, you would want to see the lensed map, and you would compare the two. In real life, of course, you only get to see the lensed map. And perhaps if I give you this map, you at first glance would not know how to distinguish it from that one. But there's actually one way in which these two maps are unmistakably different. And the way in which that is that the unlensed CMB is statistically homogeneous. If I look at the CMB here, or if I look at the CMB there, there's no preferred direction. I have no way of knowing that that patch was on the left and that patch was on the right. Whereas once I introduce the fixed lensing field, this lensing field breaks the statistical isotropy of the CMB. And in practice, what this means very practically is that it introduces a coupling between different Fourier modes. It introduces a coupling between the small and the large scales in this map. And so if you estimate whether or not there is a covariance between small and large scale nodes, if you detect that covariance, it is due to lensing. And so the way we do this, we estimate a covariance between large and small scale nodes. And because the covariance is quadratic in the temperature map. And this is why in the CMB lensing world you always hear about the quadratic estimator of CMB lensing. So again, that's just because the quadratic estimator is a way to estimate covariance between Fourier modes. And covariance between Fourier modes, again, is a symptom of breaking statistical isotropy. Okay, so this is what CMB lensing is. And you have seen the effect of it on CMB maps, and a few words about how we estimate it in practice, even though we only get to see the lens map. Now, why should one care about CMB lensing? Why is it interesting or important at all? And there are many reasons to care, because it's a powerful probe of the logical structure. Again, it tells you about the projected gravitational potential of all of matter between us and the CMB. And currently, it also already has had an important weight in the question which has to do with this so-called S8 tension you may have heard about. S8 is a parameter that tells you about the clumpiness of matter. So the higher S8 is, the more matter is clumpy as opposed to smooth. And this is a parameter that you can predict from Planck once you have measured the CMB power spectrum. So these are so-called indirect measurements of S8. You measure the CMB power spectrum, you get cosmological parameters, you predict the clumpiness of matter today. Indirect measurements. Or it can be measured directly by gravitational lensing experiments. So here's a list of galaxy lensing survey, CMB lensing experiments, and cross correlations between CMB lensing and galaxies. And you may have heard about this discrepancy where a number of galaxy lensing surveys find a value that's too small compared to the prediction of Planck. And something that's been really interesting in the last few years is that CMB lensing gives us yet another observable, another way to measure this S8 parameter. And so far, CMB lensing photospectra have not seen the real value of S8. So we'll probably learn much more about this in the next few years, and I'm sure this will be resolved. But in the meantime, I think this is further motivation for wanting other probes of the Gaussian structure, such as CMB lensing, to get independent measurements of this. Okay, so this was one of many motivations for why CMB lensing should be interesting. I now want to turn to two big challenges in measurements of CMB lensing that I and my group have worked on addressing. If there's any questions so far, yeah, please feel free. So the first challenge that I'd like to tell you about is that of extragalactic foregrounds. And the foreground in the CMB world is the way we call anything that's between us and the CMB and that emits in the microwave. And so when we use a microwave telescope to observe the CMB, it turns out we would like to see only the CMB, but what we see is the sum of the CMB and all of these foregrounds, the thermal Sunyaev-Zel'dovich effect, kinematic Sunyaev-Zel'dovich effect, which actually are those gas shadows, and I'll tell you a lot more about them in a moment. The cosmic infrared background, which is the thermal dust emission from star-forming galaxies to the universe, as well as other point sources such as active galactic nuclei that just happen to emit in the microwave. So if you don't pay attention, your CMB map actually contains all of these quantities. And these quantities are also correlated with the Gaussian structure because a lot of them are basically emissions from galaxies, which form the Gaussian structure. And so if you don't do anything to get rid or mitigate the impact of these foregrounds, what you find is a fractional bias on the CMB lensing power spectrum. So this is the power spectrum of the lensing computers for a certain multiple L as a function of that scale L. So again, it's a Fourier multiple, so these are small scales and these are large scales. And what you see here in red is for the static quadratic estimator, the fractional bias on the CMB lensing power spectrum. And that curve you should compare with the gray band, which is the statistical error we expect for something like sinus. So if you're not careful, the bias is non-zero and it's extremely significant compared to the error bar you expect in your CMB lensing measurement. So basically, if you're not careful and you let those foregrounds be in your maps, the CMB lensing measurement you're going to produce is basically complete trash. You can mess up for it out. So there are ways to deal with these foregrounds by using the fact that they have different frequency dependencies in the spectra compared to the black body of the CMB. And this is certainly helpful and it goes a long way. Another method, or class of methods that we developed instead uses the spatial symmetries of CMB lensing compared to the spatial symmetries of these foregrounds. And so let me explain, and to understand this, it helps to draw this analogy between the lensing of the cosmic microwave background and the lensing of galaxies. And so you may have heard how the lensing of galaxies is measured, the weak lensing of galaxies. And if you take the image of a galaxy, the idea would be that there's no preferred orientation. So your galaxy may have some ellipticity, but on average, the galaxy is round. And on average, the shapes of galaxies are hopefully not correlated. So if my patch of sky happens to be magnified due to lensing, the galaxy appears larger. And if the patch of sky happens to be sheared due to gravitational lensing, well, so is the image of the galaxy, and it requires some ellipticity. This is how most weak lensing galaxy surveys measure lensing. Now, how do we measure CMB lensing? I've told you about this quadratic estimator that's trying to estimate covariance between Fourier modes, or how large and small scale modes are coupled, and that may have seemed abstract. But you can show actually that the quadratic estimator of CMB lensing is doing the same thing. And so if you take a small patch of your CMB map, you can measure its power spectrum. And the 2D power spectrum of a small patch of the CMB map might look something like this. The rings you see here are the so-called baryonic acoustic oscillations. If you've ever seen the CMB power spectrum, it has bumps and ripples, and 2D is the power spectrum. And now, if that patch of sky happens to be magnified, well, in Fourier space, the power spectrum gets isotropically compressed. And if instead the patch of sky is sheared in a certain direction, in Fourier space, the power spectrum gets sheared in the orthogonal direction. And you can show that the standard method for CMB lensing, this quadratic estimator I've been telling you about, is actually measuring a combination of magnification and shear, just like one does in galaxy lensing. Okay, so that's an interesting sort of fun fact about CMB lensing. It turns out it works very much like galaxy lensing. But why is that relevant? Why am I telling you this in connection with foregrounds? The reason will become clear in a moment. And so the thing to remember is that this effect of magnification, isotropic rescaling, I can think of it as a monopole effect on the power spectrum. It has no angular dependence. Whereas the shear effect, I can think of as a quadrupole distortion of the power spectrum. And these angular symmetries, monopole and quadrupole for CMB lensing, are actually somewhat different from those of foregrounds. Because most of these foregrounds, it turns out, if I look at a map of them, what they look like are either point sources or somewhat spherical halos. And so if I ask for a given foreground, how much does it modify the power spectrum? It mostly modifies the monopole of the power spectrum, not its quadrupole. And so once you realize this, and you realize that the standard CMB lensing estimator is a combination of magnification and shear, you can actually split your CMB lensing estimator into a magnification only and a shear only. And the hypothesis would be that foregrounds should bias your magnification estimate, but not your shear estimate. And so this is a hypothesis we tested using simulation. So again, using those realistic simulations of foregrounds, this is the plot I showed you earlier with this large bias to the standard CMB lensing estimator. If you split this estimator into a magnification only and a shear only estimator, what you find is that the bias on the magnification only is actually a lot larger, which is as you would expect. You expect those foregrounds to look like magnification, but you expect these foregrounds to not look like shear. And indeed, the shear only CMB lensing estimator you find is insensitive to these foregrounds. And what's really interesting that we found using those simulations is that this works with all the different foregrounds, whereas some of the other methods, like frequency tuning, do not work as well for components where the frequency impedance is not known perfectly negotiated, or for the kinematic SZ, which has the same frequency impedance as the C. So this is a new way of coding foregrounds that uses spatial symmetries instead of frequency spectrum. And because it reduces the bias so effectively, it actually allows you to include smaller scales in your map that are more foreground contaminated and still extract lensing. And so at the end of the day, you're able to not only reduce the bias, but increase the signal to noise, the statistical signal to noise by pushing to smaller scales. So that was an exciting development. It turns out you can actually do a lot better, or differently. Let's say you have several approaches to this symmetric domain. And a class of such models is called bias hardening. I'm not going to tell you more about this, but I just wanted to highlight some of the work of Noah Saylor, grad student at Berkeley, and Omar Darwish, who's a postdoc at Cambridge. On the question of foregrounds and lensing, also wanted to highlight the work of Nishant Mishra, who was at the time an undergrad student at Berkeley, and how the methods we developed for CMB lensing might actually apply to the lensing of light intensity maps. This is the work of Abhishek Mandiyar, who's a postdoc at Stanford. And I hope that in the next few months, more will come out on this, the question of foreground biases in CMB lensing, polarization and baryonic lensing, which, if you know about this, is sort of the next generation way to estimate CMB lensing, ASIAA. So this was one of the key challenges to CMB lensing I wanted to tell you about. The question of extracting foregrounds and how we mitigate them. And I would like now to tell you about another challenge to CMB lensing that we worked on addressing. Again, if there's any question, please feel free to.
So maybe I can probably miss that. So I'm just wondering why the bias is, the value is negative. Is because loss effect dilute the signal, or?
That's a very good question. So why is the bias overall negative? And this is actually really interesting. You can ask what happens to the CMB power spectrum locally if I have an overdense region. If you have an overdense region, you tend to have magnification. What that does is it stretches your patch of the sky. And you can ask, if I stretch my patch of sky, what does that do to the CMB lensing power spectrum? And because of the slope of the CMB lensing power spectrum, this is actually a reduction in power. So, okay, overdense region reduces CMB power due to lensing. But instead, foregrounds add the power. And so your CMB lensing estimator will interpret foregrounds as a negative overdensity or underdensity. And so if you add foreground, the lensing estimator will believe this is an underdensity of matter. And that's why that line is set. But yeah, it's a really good question, and there's really good insight for what that is. Yes. Thank you. Okay, so switching to the second hurdle of CMB lensing, I wanted to tell you about the recent work of my student Dylan Shen in collaboration with me and Simone Ferraro at Berkeley National Lab. And it has to do with what we call the Gaussian noise bias. So this might be a bit technical, but please bear with me. I think I should be able to explain it, and if not, you should interrupt me and ask. So again, if I look at the CMB lensing power spectrum, so how much lensing fluctuation do I have as a function of angular scale, where small scales are here, large scales are there. The black curve here is the CMB lensing power spectrum I'm trying to measure, what I would like to see. But in practice, when I take this standard CMB lensing estimator and measure its power spectrum, what I get is not the black curve that I would like. What I get is this red curve. And so, how come? What happened? The result is that this red curve is actually the sum of the true signal I care about, plus a noise bias. The noise bias here is shown in blue. And what you can see is that on small scales of order minutes, this is n of 1,000, the noise bias starts to become much larger than your signal of interest. This is 2 orders of magnitude. So you can see noise bias is at least 10 times larger and then even more than your signal. And so what that means is when you have this noise bias, you need to subtract it. And luckily, this is something you can do with simulations of your map. This is the bias. This is something that would be there even if you had no lensing. So you just generate simulations of the CMB without lensing, and you measure this noise bias and subtract it. But in practice, the challenge is you're trying to subtract this term, which is perhaps 100 times larger than your signal of interest. And so if you want to be left with, say, 1% precision on signal of interest, you need to have modeled this Gaussian bias to 1% of a percent, 10 to the minus 4. And now this becomes intractable in practice. And this is why, for example, for the latest CMB dancing measurements from the Atacama Cosmology Telescope. The measurement stops at this value of L, about 800. This is because it becomes intractable to model this Gaussian bias well enough to subtract it accurately. So that's one challenge, and that's a problem because we would love to go to smaller scales, because this way you're increasing the resolution of your CMB dancing map. And this is also where most of the signal to noise is. So it really is a pity that we don't get to have access to these scales. So how can we improve on this? And our approach in this project has been to ask the question, instead of trying to subtract this term better, is there a way to avoid it altogether? So I hope this will not be too cryptic, but here's a diagrammatic expression for how CMB dancing works. And if you bear with me for just one slide, you'll have both understood how CMB dancing works and how this new method that we're proposing works. So remember, the CMB dancing quadratic estimator is quadratic near temperature map. And what happens is that for every Fourier mode of the dancing field you're trying to reconstruct, so for every fixed big L, for which I'm trying to measure dancing, I actually have many little L's, many Fourier modes in my maps, and each of these pair is an estimator for my long mode of kappa. So my quadratic estimator is a sum of many estimators that I can draw this way. One temperature leg, another temperature leg, where the Fourier modes add up. And so when I measure the power spectrum of this kappa instead of just kappa, I get to take all of these diagrams and stick them together. So now it's the sum over these little L's on one side and on the other side. And so we need to sum over all the quadrilaterals in my topology map, sum over the four proportions. But if I look at this sum and I ask myself which of these quadrilaterals are responsible for this large bias, it turns out a very small number of these quadrilaterals cause all of the problem. Of these quadrilaterals, some of them are parallelograms. What that means for a parallelogram is that these two vectors are opposite, meaning these are really the same Fourier mode of temperature. And as a result, I get a power spectrum and another power spectrum. So what I'm trying to say is that in the sum of all quadrilaterals, some of them are parallelograms and the others are not. All of them contain dancing information, but only those parallelograms contain the dancing bias. And so one simple idea could be, in this sum over all quadrilaterals, why do I not simply exclude all of the parallelograms? So if I do this, I've lost a bit of dancing information, but I've also lost all of the Gaussian bias. And in practice, you can ask, how much of the dancing information have I lost by doing this? And the answer is, well, what fraction of the quadrilaterals here are parallelograms? This is a question you can answer mathematically, and the answer is a completely negligible fraction. Of order, one in a million of these quadrilaterals is a parallelogram for the existing CMB experiments. So if you throw out these parallelograms, you've gotten rid of all of the Gaussian bias at basically no cost in signal tools. So this is the gist of the method we're proposing. And we tested it on simulations. So our new method here is red, and you can see it no longer is affected by the Gaussian bias. Here in green is the standard method that people have been using to subtract the bias. And in this plot, we have assumed in simulations that we knew exactly all the statistical properties of the map. And so that standard method works just as well as ours. So you can think of it as, here's just a test of our method. When everything's understood, it works just as well. And here's now a more realistic case where the map has complicated instrumental nodes in. And as you can see, the standard method starts to fail, whereas ours remains correct. So this has been the improvement from that paper led by Emmanuel Schaan, grad student at Stanford, is this very small tweak to the CMB dancing estimator method throws out a fraction, 1 in a million of the data, so pretty much no statistical cost, that gets rid of all the gas. So this is all I wanted to tell you about these mass shadows, this CMB lensing, and how to do the estimators. So how the analogy between CMB and galaxy lensing allows you to get rid of foregrounds, and how a very simple tweak to the CMB lensing estimator avoids the noise bias and pretty much no statistical or computational costs. So if there's any question on that, I'm pretty dedicated. I'll tell you about those gas shadows. All right. So moving on to those gas shadows, those scattering imprints on the CMB. What I'm trying to show, this is actually real data, is that whenever you look at the optical image of a galaxy, this little white speck, you may not see it, but you should know that there's actually a lot of gas way more extended around it, and those shadows are a way to reveal this gas. Now, why should you care about the gas around galaxies? Shouldn't we be working on dark matter and dark energy as opposed to working on the ordinary matter? Well, I think there's a lot of very good reasons to care about the gas. And to illustrate this, if you look at cosmological simulation of the dark matter here in blue, if instead you start looking at where the gas is in green and red, what you see is that it mostly looks like the dark matter, except it also has all of these fireworks going on. These explosions that you see around halos, these are supernova explosions, as well as the result of accretion onto supermassive black holes. And what these do is they expel the gas outside of dark matter halos, and by doing so, they are actually a feedback in the star formation. They regulate star formation, they make it less efficient. And this feedback is a key unknown in our understanding of galaxy formation. Just how powerful is this feedback? How efficient is it? What processes allow this feedback to occur? And so if we could constrain this feedback, we could actually learn a lot about star formation and galaxy formation. But something that makes it difficult is that when the gas has been expelled far outside of dark matter halos, and of the total matter in the universe, and we are about to try to do % precision large-scale structure measurements. So, model the clustering of matter to 1% precision. And the challenge is there's no way to model the large-scale structure to 1% if you don't know where 15% of the mass is. And so this missing baryon problem is a problem for large-scale structure. It's also an opportunity to learn about galaxy formation. And this is why I care about these baryons. Skipping ahead, these are more specifically what those gas shadows that I've been talking about really are. And so these are what happens to CMB photons as they Thomson scatter off of free electrons in the gas around galaxies and finally end up in our telescopes. There's a number of effects, and I would like to focus on three. We have experts in the room on all of these effects, Yikwan, Tepe, and others. And so if you have questions, feel free to bug them as well after the talk. The first effect, which is perhaps the simplest to understand, is simply a Thomson scattering off of an electron, even if the electron was static. And so how much screening do you have is directly proportional to the density of the gas. So if you can measure this gas shadow, you will learn how much gas there is. The other effect, those Sunyaev-Zel'dovich effects, are what you see when the scattering occurs off of a moving free electron. And so the free electron can be moving for two reasons. One, because it's hot, and so it has thermal velocity. And so in that case, you get the thermal Sunyaev-Zel'dovich effect. That effect is proportional to how much gas you have. So if you had no gas, you would have no effect. And it's proportional to the temperature of the gas, which is effectively the average V squared thermal. Now, another reason why the free electron might be moving is if the whole halo has a bulk motion, and the corresponding effect is called the kinematic SZ. It is again proportional to how much gas you have, because if you had no gas, you'd have no effect. But it's also proportional to the size of that bulk velocity of your halo.
Now, these effects here are ordered in order of size. And so the thermal SZ is generally the largest effect. And one way to detect it, and people in the room have done this, is through a stacking analysis. And so you take a cosmic microwave background map around the position of the galaxy. So this is the size of the inner pixel of my map, which is a half arc minute. And if you look at your CMB map around this galaxy, what you might see is an image like this. And if you stare at it, there's really not much to see. This is basically just noise. And what it says is that the signal is too faint to be seen around a single galaxy. So one way to go around this is to not look at just one galaxy, but to stack, to average your signal around many, many galaxies. This way, the noise goes down. And so as you add more and more galaxies, in fact, hundreds of thousands of galaxies, that shadow around the galaxy starts to appear. Now, to orient you a little bit, this inner circle is the typical resolution of our CMB experiment of order arc minute. And this outer circle is the extent of the dark matter that we expect around those galaxies. It's the virial radius. And what you can sort of see is that you already do detect gas outside of the virial radius. So again, this is the thermal Sunyaev-Zel'dovich effect. It tells you about the product of how much gas times the temperature. So it tells you about the thermal energy of the gas, which is a relevant thermodynamic quantity. How do you instead measure this kinematic SZ? It'd be interesting to have both, because if you have both, and if you know the bulk velocities, you're now able to separate density and temperature. So you not only know how much thermal energy is in the gas, but you know where it is and you know what the temperature is. Well, one challenge here is that because this is a Doppler effect, the effect changes sign depending on whether the bulk motion of the halo is away from you or towards you. This is very much your gas being a tennis racket and the photon being a tennis ball. If the racket is moving towards you, the tennis ball gains energy, and so it's a positive effect. If the tennis racket is moving away from you, the ball is effectively slowed down, and it's a negative effect. So if I just stack temperature maps at the position of galaxies, because on average galaxies are equally likely to move towards me or away from me, the effect will be 0. So to avoid this, what we use is an external handle on the velocities. And that external velocity handle is what we call velocity reconstruction. The fact that in linear theory, if you assume mass conservation, there's a one-to-one relationship between the velocity field and the density field. And if this differential operator is not super intuitive, really the intuitive content of this equation is that if I have more mass here, it's because the mass has been moving towards it. So this is very simple linear theory mass conservation, and it turns out it works extremely well. And so you can use this equation to get an estimate of the velocity field based on the density field. In practice, it looks something like this. So these are boss galaxies, hundreds of thousands of them. Each dot is a galaxy. You are sitting here at the center, looking at all these galaxies in the CMB. And color-coded in blue and red are this reconstructed velocity along the line of sight. And so now that for each galaxy you sort of know how it's moving, you can stack at the position of your galaxies weighted by the velocity. And now you no longer have this cancellation of sign. And so what you get when you do is an image like this, where this little blip of bright color here really is actually a 6 to 8 sigma detection of the KSZ effect, which at the time was the highest significance one. And so around those galaxies, you now have access to the thermal SZ and the kinematic SZ profiles. And so you can measure where the gas is, how hot it is. You can show just how far the gas extends, which turns out is much farther than the dark matter, and this contains information about feedback. Because of time, all I will say is that the DAISY data is really going to transform our ability to do this, because we're simply going to get way more galaxies with redshift, and our signal to noise scales as square root of number of objects. And so the DESI data that we have at the moment is really exciting for this, and there's a number of projects going on. I just wanted to highlight the work of my graduate student, Bernardita Reed-Guachaya at Stanford, who is currently leading KSZ measurement with Acton DESI, whose signal to noise should be way better than the one I showed you a few minutes ago. Finally, because of time, I'll skip forward and just say that this patchy screening effect had actually not been detected until a few months ago. And this detection was done in our 2 papers here, led by grad student Theo Schutt and Abhishek Maniyar, whom you saw earlier, as well as postdoc Will Colton at Cambridge. And so this set of 2 papers is a theory paper where we derive a new estimator that made this detection possible, and then the first detection in ACT data. This is really fun stuff, and I'd love to tell you more about this, but I think because of time, I need to wrap up. So feel free to ask if you're interested. So inclusion about these gas shadows, these scattering imprints of the large-scale structure on the CMB, they are interesting because they can help cosmology by telling us where the baryons are, where the ordinary matter is. Again, that's important if you want to do 1% large-scale structure, because you need to know where 15% of the mass is. It's also a useful input for feedback models in galaxy formation. And just wanted to flash that first detection of the patchy screening. So I'll stop there. Thank you very much for your attention, and I'll take any questions.
Okay, questions for Emmanuel?
Yeah, thank you for your talk. So I actually have 2 questions. So the first one is about the feedback. So you mentioned that the gas extends outside of dark matter, and then you mentioned that it's probably due to feedback. I just wondering whether or not there are actually other mechanisms can push gas. These are all hot gas, right?
Mm-hmm.
So I'm just wondering whether or not there are other mechanisms can produce this kind of signatures.
Yeah. So no, that's a really good question. So the first thing that makes the gas different from the dark matter is the fact that gas has pressure, thermal pressure. There's also other sources of pressure, like cosmic rays, for example, or magnetic field. But here in this case, we are actually able to detect gas several times the virial radius. And that far is kind of hard to do without those powerful explosions, AGN, active galactic nuclei, for example, or supernova. One reason we're interested in measuring those gas shadows around galaxies as opposed to massive clusters is also the fact that when you're in lower mass dark matter halos, the gravitational potential is not too deep. And what that means is it doesn't take a huge amount of external energy injection to push the gas very far out. And so in a sense, those dark matter halos of low mass are a good place to look for the effect of feedback, because there's the place where the response of the gas will be maximal to feedback. And so that's sort of our motivation. Yeah. Thanks.
And actually, the second question is about the SA tension. So I thought that the CMB lensing and the weak lensing measurement, they are affected by a similar large-scale structure, right?
Mm-hmm.
Although the CMB lensing, the kernel, I think it's more sensitive to redshift 2 region, if I remember correctly, but the weak lensing with current surveys such as hyperspring case, probably redshift lower
than galaxy lensing. So this might be a high versus low redshift discrepancy. The other one is that CMB lensing at the moment probes larger scales than galaxy lensing. So I showed, for example, this cutoff at high L small scales due to the Gaussian noise bias, but there's other reasons. And yeah, cosmic shear measurement tend to be sensitive to very, very small scales. And these are scales where the effect of baryons should be most important. And so this is sort of the motivation for looking at those baryon profiles with SZ. If we can calibrate the baryonic effects on the matter power spectrum, we might be able to change the modeling of these. So yeah, slightly different redshifts, slightly different scales.
Thank you.
Mm-hmm. Thanks a lot.
Thank you for your talk. And I'm wondering that with the mass shadow influence the gas shadow or vice versa?
Right. So can you have both at the same time, for example? Maybe that's the question, or?
Yeah. So how do you decompose these two effects?
How do you separate them? How do you disentangle them?
Yeah.
Right. That's a really good question. So there's several ways to do that. I think maybe the simplest way to answer this is the spatial symmetries are different. So, for example, when you have a gas shadow, you get something in your temperature map that's correlated with the position of galaxies. So typically, you might stack up the position of galaxies and you will see that effect. In the case of lensing, the effect tends to be correlated with the direction of the unlensed gradient. And the reason for this is lensing is a deflection. So if I move the CMB across the gradient of temperature, I do not cause any change of temperature, and so you will not see this. So the only displacements you see are along the gradient. And so basically, the effect of lensing depends on the size of that local gradient and its orientation. So that's one way to distinguish the two. Then some of these gas shadows can change sign. In the case of KSZ, I mentioned they change sign based on the direction of the bulk velocity. In the case of screening, they change sign depending on the large-scale primordial temperature map. So basically, all of these signals have slightly different angular symmetries, and they may change sign differently. Another important thing I should mention is they also may have different frequencies. So lensing just displaces pixels. It doesn't change the spectrum. Same for KSZ. Same for patchy screening, but it's not the case for thermal SZ. So between frequency, angular symmetries, and correlations with different quantities, you sort of get what you need to disentangle them. I hope that helps.
Okay, thank you.
Cool, thanks.
So I'd like to ask more about this screening SZ. So I guess, so because this effect is probing the kind of gas density directly, and so at the end, are you probing the just omega n or a combination of omega n sigma 8 or something else?
Right. So yeah,
like omega baryon.
Yeah. My hope with those measurements of gas shadows, TSZ, KSZ screening, is mostly to localize the baryons and then use that to know what the power spectrum looks on small scales and how to best model those galaxy lensing surveys. But you are right. The nice thing with it is that you have a measurement of gas density not affected by temperature, bulk velocity.
Yeah.
So that's a clean measurement of temperature. The drawback is that this effect is smaller than the others by a factor of about 10. One other motivation is if you can combine the two, KSZ and screening, you can remove the gas density in KSZ and have a clean measurement of velocities, which would be really cool. I don't know if that answers.
Okay, yeah, I see about this later.
Sounds good. Thanks.
So any more questions for Adu? Okay, if not, I guess we have coffee and tea served outside, and people can ask more questions to our speaker. And let's thank our speaker again.
Thank you very much.